Okay. All right. So, evening, everyone. Before we go into interference, okay. I found these two slides that I don't think that I mentioned to you guys previously. All right. Because this is an application of diffraction of sound, so I thought of explaining this a little bit. All right. So, let's just say, for example, if you are blocked by a wall, someone is talking, or there's a radio over here, all right, and there's a cleaner or students located at the other side of the wall. All right, so normally it says that a cleaner can hear the sound of the radio placed nearby a corner of a wall, but he cannot see the radio. Why? All right, because the explanation here says that the cleaner can hear the radio even behind obstacles. All right. In case that this question comes out, all right, in SPM or in exam, whichever exam it is, okay, no specification. Now, in case that this question comes out, how do we identify? Obviously, one thing, this is an explanation question, so probably it's going to be question C or question D. Okay. So over here, what you have to identify is identify the keywords in the question. What are the keywords? Okay, for me, the word sound. All right. In physics, Form 4 and Form 5, there's only one chapter that is related to sound, and that would definitely be the wave chapter. So sound wave, all right, it's over there, definitely here already. And then, but he cannot see the radio because he's actually placed at a corner of the wall. Corner of the wall is actually an obstacle. All right, so when we talk about a wave, we have four phenomena. We have reflection. All right, reflection whereby the sound is supposed to bounce back. We have refraction. All right, but refraction, we don't, when we talk about sound wave of refraction, we are talking about hot and cold temperature. All right, so at daytime, wave refract towards the sky, and at night, sound wave will reflect towards the earth. And then we have diffraction right now, so far that we have learned. All right, diffraction is actually when a wave reaches an obstacle. The wave can actually propagate to places that it's supposed to be blocked. So that's diffraction. All right, and what we're going to answer today is actually interference. So interference is very, very obvious difference compared to the other three. Later on, you will know. So this question here is a obvious diffraction question. Now, the question asks us why. All right, so this is a 4 to 5 marks question normally in application. All right, explanation here is the cleaner can hear the sound, hear the radio even behind obstacle. Obstacle giving cue that this is a diffraction. And make sure, which means that we have to mention the word diffraction of sound wave inside the question. So the sound from the radio to spread around the corner, all right, the keywords here, sounds from the radio to spread around the corner of the wall is because of diffraction of sound wave. Okay, the wave will experience a diffraction when passing through a single aperture or a round obstacle. Okay, so sound wave are more easily diffracted compared to light wave. For me, this one tak payah, number 4. All right, this is because the wavelength of sound, all right, this is correct. The wavelength of sound is much more larger than the wavelength of light. Oh, okay. Now I understand why they compare with light wave. Because the question says, but he cannot see. We can only see if the light wave propagates. All right. So we cannot see the light the light ray from the arrow directly to the eye of the cleaner. So that's why they compare sound wave is more easily diffracted compared to the light wave. All right, because over here wavelength of the sound is much larger compared to the wavelength of the light. Okay, so that is one applications of diffraction of sound. All right, next is actually a marching band. All right, this question came out before, I think a few years ago, if I'm not wrong, in the previous syllabus, KPSM syllabus. So if a marching band is approaching on a cross street, right? There's walls, there's buildings over there, all right? Which instruments will you hear first? One is a piccolo. The other one is very obvious, is a drum. Okay, so the question actually asks which instruments will you hear first? Will you hear the piccolo first, or will you hear the drum first? All right, now the bass of the drum is actually low pitch. So you'll have to write this down because sound wave subtopic has been taken out from your syllabus already. Now, high in terms of sound, all right, sound wave, we always have high frequency. All right, when we have high frequency, it actually corresponds to high pitch. All right, high frequency will correspond to high pitch. You know, some people when they talk, the sound is actually very sharp, very high. All right, you will always say why the pitching so high. It's because the frequency is actually quite the frequency of the person's sound wave, all right, is actually quite high. So low frequency will correspond to low pitch. So you better write this down because I'm gonna take it down, erase this off already. Yeah. Then after that, another part of sound wave is actually loudness. Higher loudness, all right, high loudness will correspond to high amplitude. All right, low loudness will correspond to lower amplitude. You know, amplitude of the sound wave. All right, what you normally do, the tuning that you usually do to your headset or to your uh those playlists, all right, that one you actually modify the loudness. All right, you either make it louder or you make it softer. All right, that is when you actually change the amplitude. When you are actually talking about someone who's talking very sharp, or someone's voice over the mic is actually quite low, all right, so that will be low frequency. All right, so low pitch, low frequency. If it's loudness, high loudness will correspond to high amplitude. So I'm going to erase all this right now. Okay, so the question here says that low pitch bass drum has long wavelength. Low pitch bass drum means low frequency. How did low frequency actually corresponds to the wavelength? Because both is actually sound wave. So when there is sound wave, it travels at the speed of light. So V equals, speed of light, but sound wave speed. So wave speed equals to frequency multiplied by the wavelength. Both is traveling using the sound speed of the sound wave. So V will be a constant value. So frequency will be inversely proportionate to the wavelength. It doesn't matter if it's sound wave, light wave, or water wave, the frequency will be inversely proportionate to the wavelength. So because the bass of the drum is actually low pitch, which means the frequency of the bass drum is actually low, and hence the wavelength is actually higher. All right, so that's why low pitch bass drum has longer wavelength. High pitch piccolo has a shorter wavelength, which means that the frequency is actually high. When the frequency is high, then the wavelength would be shorter. So high pitched sound tends to be more directional because they don't diffract much. All right, that's the reason why what you see over here, all right, the piccolo sound will actually travels in a straight line. This is the obstacle. All right, this is the obstacle. Because high pitch is lower frequency, shorter wavelength, so it actually goes in front more obvious. That's why it says more directional because they don't diffract much. Therefore, the first sound that we will hear normally is the bass drum being heard. Bass drum wavelength is bigger, longer. All right. So in this case, they will actually be easily diffracted by the buildings. All right. So I hope this explains to you guys. There's no number 5 over there. Okay. So I'm going to go into interference of light wave already. Okay. So interference of light wave, previously this one has already been sent out. I'm just curious, is there any form 5 in this group? Because I think I did not send into the form 5 one. All right, I didn't really send this PowerPoint slide to the Form 5. Is there any Form 5 who wants it here? You better voice out so that I can actually forward it in. Okay, so interference of wave. Here is a principle of superposition of wave. We have actually, Li Xuan is over here. All right, class, give me a quick minute. Let me just forward to Li Xuan for a while. Very quickly, just give me a quick minute. Li Xuan, I already sent inside the WhatsApp group. Okay, now interference of wave. What happens here is that the wave we are talking about is actually here, all right? The water wave that you can see is that one is actually be created by the swan on the front, and another wave is actually created by the swan at the back. All right, so over here, the principle of superposition states that when two wave overlap, the resultant displacement is the sum of the individual displacement of the two wave. So number one, all right, this sentence of principle of superposition is the definition. All right, so please highlight that, underline that in the book. All right, so principle of superposition states when two waves overlap. All right, when it overlaps, the resultant displacement, each of the wave will have its own displacement. So the resultant displacement is the total sum of the individual one. So what does this means? Okay, let's see what else do I have here. Okay, I'm gonna show you guys slides here. All right, so that's interference. All right, so this is interference of water wave, if I'm not wrong. Okay, all right, this is interference of water wave. So I'm just gonna click this one time. The minute I click this one time, it will actually drip water down. So, all right. So what you will see over here, all right, is we have a pipe, tap number 1 and tap number 2. They are dripping water down onto the water wave. And if I were to see it from the side view, can I see this from the side view? Tak boleh. Okay, so when we actually see this, when it drips down, all right, let me go back. Separation. Okay, I'm just gonna drip one first. So when a single pipe actually drips down, it will create one wave. Recalling back, the bright fringes is actually the crest of the wave, whereby the black one, all right, this is what we call fringe. All right, bright, this is actually the bright fringe. If it's a single wave source, all right, the source is actually the pipe. So if it's a single wave source, this is a bright fringe, and then this is a dark fringe. The bright one will correspond to crest of the wave, whereby the dark one corresponds to the trough. All right. So what happens here is that this is only a single source. But if I were to drip both together, all right, when I drip both together, the top source will actually create one wave, and then the bottom part will create another wave. And what I want you guys to see is actually, do you notice this part is a little bit blur? All right, this part is a little bit blurred. So what I'm going to do is I'm going to have this graphed over here. This is different from what I have last time. How come? Okay, so you can see that when it drips down, you can see the amplitude over there. There's damping here. Okay, so what we have is we can see that the interference happening. All right, I'm just going to take this away. All right, this part, okay, do you notice this blur line over here? This is actually where there is a destruction happening. All right, destructive happening. I'll explain that in a short while. So in case of a light wave, so if it's a light wave, all right, they will interfere together, assuming this is a laser pen. All right, they will interfere this together, and on the screen, okay, On the screen, they will actually create a interference pattern. All right. Interference pattern is whereby one wave interfere with another wave. They will actually superimpose each other. All right. When it superimpose each other, they will actually have a constructive interference and a destructive interference. So what happens here is if you see this blur line over here, it will at the screen part, we will see a dark fringe. Right. This is where destructive interference happen. And the bright part is actually where constructive interference happened. Okay, so this is actually for light wave. So in case of sound wave, right, in the terms of sound wave, what will happen over here? Okay, I'm not going to see the graph. Let's see, particles, dana. All right, so in case of sound wave also, it does have the destructive and constructive interference happening. All right, so I keep mentioning what is constructive and destructive. Let's go back to the slides and explain a little bit further before we come back into this this simulation in order to play around with the simulation more. If any one of you wants to play with the simulation later on after the lesson, please do let me know. I can just share the link to you guys, all right? Okay, so let's go back to our PowerPoint slides. Now, first thing first, we have to understand regarding interference. All right, before we go into constructive and destructive interference, we have to know what does interference means. How does interference occur? First, interference occur because when two waves meet when propagating along the same medium. All right, so this sentence is saying that for interference to occur, you need two waves. Reflection, refraction, diffraction can happen on its own with one single wave, but interference must have minimum two waves. All right, so and it has to be along the same medium. So if you recall previously, I mentioned that when we talk about the phenomena of wave, we have to talk about the wavelength, we have to talk about the frequency, we have to talk about the wave speed, all right, and we have to talk about the direction. Okay, so wavelength is affected by the medium, frequency is affected by the source, wavelength is affected by frequency and wavelength, and direction, obviously all the phenomena will actually cause the direction to change. All right, so here interference saying that there's two wave meets while propagating along the same medium, which means the wavelength is going to be the same. Okay, so when the two waves superimpose means to overlap. If you recall back right now in when we were having class in the physics lab, our school is very, very near to the Subang airport. So every single time a plane passed by the school area, all right, pass by, that means fly over the school area, you will notice that I always keep quiet. Or when the bell rings, I will always keep quiet. Why? Because my voice through the speaker is actually projecting out a sound wave. The school bell or the sound of the plane flying over our school, that is also another source of sound wave. So if I were to talk the same timing the bell and also the plane is passing by, interference will occur. My voice will superpose, which means overlapping. Superpose means overlapping. All right, so my voice will actually superpose with the sound of the bell or the sound of the plane flying by. Or for another example, my voice is superposed with your background music right now. Okay, so what happens over here is that when two waves superpose, it will either be constructive interference, which means it will create a louder sound. All right, so constructive means it will create a louder sound, or destructive interference, which means it will create a softer sound. Okay, so over here, the key for SPM level, for these two waves to overlap, to superimpose, all right? Superposition, superpose, it's all the same thing, take note. So for the condition of this two wave to actually interfere, to superimpose is actually coherent sources. So this is one thing that you guys have to take note of. Coherent sources are coherent sources are sources that produce wave having the same frequency and the same constant difference. All right. So what it meant is that wave number one and wave number two will always be in the same distance from each other. Okay. So that's one thing that it's meaning. And the second one, it has to be the same frequency. Okay. So one quick question, if you recall back, in terms of my voice and also the school bells sound, we know definitely that my voice is different. The frequency of my voice is different from the school bell. All right, but does interference occur? Yes, it does also. All right, because it overlaps my sound. But then, all right, in terms of idealistic, remember, whenever we're talking about textbook, we are talking about idealistic case. In terms of idealistic case, they are talking about the interference to occur. The best interference to occur is whereby sources that produce wave that have same frequency and constant phase difference. Okay, so I hope that explains regarding coherent sources. The top part is actually from my own notes, not my own notes, my previous notes that I use. The bottom part here is actually coming up from the Form 4 textbook. Interference of wave is a superposition or two or more waves from a coherent source of waves. All right, so that is the definition for interference: superposition of two or more waves from coherent sources. So the two sources of waves are coherent when the frequency of both waves is the same and the phase difference is constant. All right, so this is almost similar to what I have over there, but definition wise, we will always follow back to the textbook. Okay, so let's see. This is actually a ripple tank. All right. The ripple tank consists of here. All right. We have a spherical dipper, either spherical dipper or we have a plain dipper. All right. Then when two spherical dippers, you need to have a lamp here. All right. A light source. This is actually a generator over here that will be connected to a power supply and a rheostat for the purpose of providing electricity, because we have a motor over here. All right, that's the motor location. This motor will actually cause the dipper to vibrate at a certain frequency. Okay, so when it vibrates at a certain frequency, we will have the interference pattern. We will have the interference pattern like this. All right, we will have this interference pattern on the ripple tank. So that's why I took this simulation to show the ripple tank. All right, so if we increase the motor, it will cause the pattern to change. Okay, so they will definitely cause the pattern to change. So if you were to slow it down, the interference pattern will change. So later on, we will explain further regarding this interference pattern. Okay. Now, so we have a stroboscope over here. All right, so please do take note. Stroboscope, if I'm not wrong, it's not written inside the textbook, but a stroboscope, spelling Stroboscope, stroboscope. All right, so a stroboscope main function is actually to freeze a moving object. Right, kind of similar with what we have on our handphones that actually use a slow motion camera. All right, it's actually to slowly freeze down the moving object. The key for you to slow down the to slow down the moving object is that the stroboscope must be turned. All right, that's why there's a arrow here. The stroboscope must be turned with the same frequency as this particular motor. All right, then you will see the image being frozen. Okay, image being frozen, which means that instead of seeing an interference pattern like this, it will stop like this. All right, instead that you see the wave moving. All right, when you use a stroboscope and the frequency matches with the motor's frequency, the image of the wave actually freezes when you know. All right, what you see actually freezes. If you have the time, I think I'll show it to you guys later on. Um, Form 5 already, if I'm not wrong, almost every single class I showed it out already. Okay, so that is regarding interference. Now let's talk about superposition. All right, superposition of two waves. We're talking about two waves right now. So we have wave P, this is in the textbook. We have wave P and wave Q. Both of it is located at the crest. So this is actually the crest of wave P and the crest of wave Q. The amplitude of the wave is A. All right, so before superposition, which means before overlapping. So once it overlaps, all right, during the superposition position, I'm using the word overlap so that you'll understand, but the physics term is actually known as superposition. So during the superposition, initially amplitude of Q is A, amplitude of P is also A. So during superposition, it will actually rise up to becomes 2A. Why? Because it adds up the amplitude from wave P and it adds up the amplitude of wave Q. All right. Then after superposition, they will move back to amplitude A. All right. They will move back to amplitude A. So when the crest overlaps a crest, we will have a constructive interference pattern occurring. All right. This is a constructive interference pattern happen for two crests. So what happens if, let's just say, previously we talked about a wave having a crest and a trough. All right, so this part is actually the crest, and this part is actually the trough. So what happens when a trough overlaps a trough? It will also be constructive interference. All right, so constructive interference also happens when two troughs are in superposition. So we have amplitude is also A, but this time because it's going downward, so that's negative, right? And then here is also negative A. So when it superimpose, all right, when it's superposition superimpose, it will become negative 2A. Negative A from wave P and negative A from wave Q. So when they overlap, it will become negative 2A. Then after superposition, it will go back on its own path with the same amplitude of negative A. Okay, so this is also a constructive interference pattern. Okay, so let's go to the next slide. I hope you guys are okay. All right, destructive interference. Destructive interference means it will become zero. All right, it will become zero. So destructive interference when a crest and a trough are in superposition to produce zero combined displacement. So a crest from P, that's positive A, and then a trough from Q, which is negative A, when they overlap, A plus negative A will become zero. All right, so that's why it's called destructive. All right, a positive and a negative, it will become a zero. But after superposition, it will still become back to its original positive A and negative A. All right, so in short, constructive interference, louder for sound wave, brighter. Okay, let's just write this. All right, so constructive interference is when one, a crest plus a crest, or number two, a trough plus a trough. All right, that's constructive interference. So in terms of light wave, all right, in terms of light wave, constructive interference would be even brighter. In terms of sound wave, it would be louder. In terms of water wave, it would obviously be higher. All right, so that is actually for constructive interference. If we are talking about destructive interference, all right, so either screenshot or write this down as quick as possible. Okay, I'm gonna erase everything off right now. In terms of destructive interference, all right, so which means a crest of one wave overlaps a throw of another wave. So I'm going to put this too many T already. So for light wave, it will become dim or dark. If it's for sound, it will actually become softer. All right, if it's talking about water wave, it actually becomes calm. The wave is calmer, which means the amplitude is actually quite there's no amplitude at all. All right, so that's destructive interference. Okay, so hurry up, changing slides in 5, 4, 3, 2, 1. All right, so interference of wave, constructive interference. Where is my okay? All right, constructive interference occurs when two waves of the same phase, right? Same phase, which means both is at crest or both is at throw, coincide to produce a wave with maximum amplitude. Maximum amplitude doesn't only not only meaning means positive, all right? It also means negative direction also, all right? So destructive interference is when two waves that are out of phase. Out of phase here means the crest of one wave and the throw of the other wave coincide. Notice here, in phase, same phase means two crests or two throws. Out of phase means a crest of one wave with the throw of the other wave. All right, so please take note on that. Now, thus cancelling each other out with a resultant amplitude equals to 0. Now, example for it here, all right, there is a source. The source is located here, all right? You guys have the actual PowerPoint slide, so you will be able to see that clearly. So over here, the solid line represents the crest. Watch this. Wave fronts, all right, represents the crest. Solid line represents the crest. The dotted line represents the throw. Please do take note from 4 and from 5. All right, solid lines represents the crest, dotted line represents the throw. So if you look at the interference pattern over here, why the interference pattern is located here? Because this is where this wave, the wave from the first source and the wave from second source is actually overlapping. So let's take attention, for example, over here. All right, at this point, all right, the wave from the first source, solid line, overlaps with the solid line of the second source. So this is a crest overlapping a crest. So when a crest overlaps a crest, this is a constructive interference. Or if you look at this point over here, this is a dotted line overlapping with the dotted line of the other wave. So when two dotted lines overlap, it means that a throw overlaps a throw. So that again is a constructive interference. So this red line over here represents the constructive interference line, or to be exact, we call it the anti-node line. Anti-node lines is a point where the constructive interference occurs. Okay, then after that, we have the destructive interference. Now, where is the destructive interference? Destructive interference is where a crest overlaps with a throw. So, which means a solid line overlapping with a dotted line. So, over here, let's find here at this position, there's a solid line overlapping with a dotted line. Here also, solid line overlapping with a dotted line. So this line is called a node line. A node line is when a destructive interference occurs. Okay, so now let's look back into the simulation that I showed just now. All right, so if you notice here, this blur line over here, can you guess this blur line is constructive or destructive? Do guess inside the chat box as usual. Is this blur line constructive interference or a destructive interference? Yes, good. It's actually a destructive interference. Now, please do take note when you answer in exam, all right, whether it's end of the year, your next year, mid-year, or for the Form 5 is your SPM, please remember to write in full destructive interference. All right, don't just write destructive. Same thing like your units. All right, you write the value, no unit, no marks. Okay, now, so this is actually for sound. Let's look at light. All right, so over here you can see this blur line is actually destructive. That's why on the screen it's actually dark. All right, destructive interference. That's why here this is actually a dark fringe. Here is a bright fringe. All right, because it's a constructive interference happening. All right, the image that we see on the screen, this is the screen, see? The image that we see on the screen, the bright one, we call it as a bright fringe. The dark, we call it as a dark fringe. How did a dark fringe occur? Is because destructive interference happened. How did a bright fringe occur? It is because constructive interference happened at that line. All right, so please do take note. Okay, so destructive interference is a node line. Constructive interference line is actually the anti-node line. All right, so let's go. Now, Young's double slit formula or Young double slit experiment, Form 5, you would hear it again previously, all right, when we talk about quantum physics. So for Form 4, this is the first time you're hearing it. Interference experiment is actually found by Young, a scientist named Young. I've forgotten what's the other name already. So we always keep saying it's a Young formula, Young double slit experiment. It's actually an interference experiment. Because for refraction, refraction, diffraction, there is no specific names. All right. But for interference, we have interference pattern is called experiment is actually the Young's experiment. Okay. Now, so please do relate when you hear the word Young experiment, this is the interference of wave. If I'm not wrong, the other special name that we have in a wave chapter is actually resonance, where we have the Barton's pendulum. All right, so that is actually for resonance. Now, Young double slit experiment, what do we have to take note? Young double slit experiment gave us the relationship, the last formula for this chapter that relates the wavelength A, X, and D. So I'm going to explain to you what is A, X, and D. Now, A, all right, this is a general formula. The formula is lambda equals to AX over D. All right, so over here, lambda is actually the wavelength of the wave. All right, whether water wave, light wave, or sound wave. All right, so lambda is actually the wavelength of the wave. A is the distance between the two coherent sources. All right, so from source 1 to source number 2, the distance between these two sources is actually using the symbol A. X is the distance between two consecutive node lines or anti-node lines, which means if there is a screen over here, it will project out. All right, the distance between them. In a short while, I'll use back the simulation to show you guys. So after that, D, capital D, cannot small d, cannot capital A, cannot capital X. All right, it have to be small a, small x, and capital D. So capital D is the distance between the source to the point of the measurement or the screen. So let's have a look over here to the simulation. So we have lambda equals to AX over D. Let's go back to the simulation. Now here, this simulation, all right, we have these two sources. So this 2 is actually our A. All right, the distance between two sources, because this is actually where the source of the first light and the source of the second light wave occur. So between them, this is actually the symbol small a. Now, capital D is actually from this source up until this location, because this is my screen over here. All right, if I don't have a screen, I have no idea where am I measuring it. So if I were to put a screen from the source up until the screen, that is our capital D. Distance from the two coherent source to the point where we are measuring it. But what is X? Where is X? X is actually located over here. All right, this is the destructive interference pattern. This is the constructive interference pattern. So, all right, over here, what we can see is a. Give me one quick minute. My laptop want to know battery already. I did notice I didn't switch on my power supply. So my X here is actually from here. You see, this part is actually the destructive interference. Here is also my destructive interference. So my X is actually from this location, all right, the destructive interference to the next destructive interference, or from one constructive interference to the other constructive interference. All right, so that is the distance X. Okay, so please do take note. This is a very, very famous phenomena that they keep asking. All right, so out of reflection, refraction, diffraction, and interference, interference is the only phenomena of wave that has a formula. All right, so when you see lambda equals to ax over d, this is actually the formula for the interference of wave, and also known as the Young's double slit experiment. All right, so what factors affects the interference of wave pattern? So the wave pattern will change depending on the value of x. All right, x means the distance between two consecutive. Please do take note. X is the distance between two consecutive nodes or antinodes. What happens if you don't write? If they ask you what is x, you're going to write distance between two nodes or two antinodal lines. I can tell you, you will get 0. Why? The keyword for x is actually consecutive. Consecutive means continuous. All right. So let's just very quickly, let me show you. All right. What happens if you don't write x? It means that I can measure the distance from, I'm going to use green, the distance from this first antinodal line to this antinodal line. When you don't use the word consecutive, you just mention the distance between two node on two antinodal line. It means that you can jump, So when it meant x is the distance between two consecutive node or antinode, which means directly the next line. All right, so please do take note. Okay, so now the interference pattern depends on the value of x. So how can we change x? So from the formula itself, okay, when x, for example, this one, please do take note on this graph. So x is directly proportionate with the wavelength, okay, means that in this situation, the distance and a is fixed. When the distance between the source and the distance between the two coherent sources is fixed, as the wavelength increases, x will increase. When x increases, we will actually see less pattern. Take note. When x increases, we will see less pattern. How does it mean? Okay, so here we're going to change the wavelength. I'm going to show you the simulation right now. Okay, so right now, I'm going to fix the A. We are going to observe the X. I'm going to change the frequency. How am I going to change frequency of light wave? Is actually from here. All right. So red light has lower, more wavelength. Higher wavelength means lower frequency. So violet has higher frequency, shorter wavelength. So watch what happens when I increase the frequency. Here I can see 3 constructive interference or 3 antinodal lines. So when I increase the frequency to blue, all right, I've just increased the frequency. Just now with green color, I can see 3 constructive interference. All right, so right now, let's see how many constructive interference can we see at the same screen. I still see 3, all right? But look at whether the distance have changed or not. So I'm going to increase it some more until violet, until the very end. Oh, no wonder so slow. Let's make it a little bit faster. So here, wait, did I analyze correctly? Yeah. Wavelength, wavelength increase. I'm going to show you guys frequency increase. So sorry. Okay. Let me go back to PowerPoint slideshow. It's better for me to rewrite what I'm going to show you so that I don't confuse myself. Okay, so lambda equals to AX over D. So right now, I am letting A, right, distance between the source and distance between the source and the screen to be constant. So which means that my wavelength will be directly proportionate to my X. My wavelength will directly proportionate to X, which means as the wavelength increases, my distance X will increase. But also one thing, because wavelength increases, frequency will decrease. Okay, now in terms of the rainbow color, the highest color is actually red color. Red color has the highest wavelength. It has the lowest frequency. The bottommost color is actually violet. Violet has the lowest wavelength, highest frequency. Okay, yeah, so just now I analyzed frequency, sorry. So here, if I want to increase the wavelength, which means I have to move towards red color. Okay, when I move towards red color, my wavelength increases. All right, if in question, can you write lambda increases? I will tell you that's not true. Please write the word wavelength. So when my wavelength increases, my X will actually, the distance between the 2 consecutive node lines or anti-node lines will actually increase. But when it increases, the patterns that we see, all right, we will see less patterns on the screen. All right, we will see less patterns on the screens. Okay, so over here, let's go back to our simulation. Okay, so I went the other opposite direction. Let's go. This is green color again. Once again, green color. Okay, so we have 3 interference pattern. Look at the position. Okay, I'm gonna sengaja put this here and put the other one over here. All right, so my distance between 2 consecutive antinode lines is 1740.5 nanometer. So that would be 1.75 times 10 to the power of -7, like that, -6, okay, meter. All right, so I'm going to fix that and I'm going to change to red color right now. This was my initial X, all right. So I have increased the frequency and notice that it no longer, the second constructive, all right, or the antinode line is no longer at this location. It has already increased, all right. And when it increased, do you notice that the number of patterns that we observe is already less. All right, the number of patterns that we observe is already less. So this is actually in line with what we explained over here just now. All right, so let's look at violet. All right, let's analyze back with violet. So when we change to violet, when the wavelength decreases, the frequency of the light wave increase. So lambda decrease. All right, lambda decrease, our x value will decrease. When x value decrease, we should see more patterns. All right, we'll see more patterns on the screen. So let's see whether this hypothesis coincide or not. So I'm going to go all the way to violet right now. All right, so this is my original x green color line. And you can see right now, the x has really decreased. And look at the number of patterns. Just now we see only mainly 3. When we go to red, all right, the side ones we only can see half, but over here, do you notice you can see 1, all right, 1 constructive, 2 constructive, 3, 4, and 5. We see more interference pattern already. All right, so this is what it meant for this particular slide. All right, so this is when x increases, the wavelength increases, the interference pattern also, the distance between the 2 constructive node line or anti-node line increases. So I'm going to go to the next analysis. The next analysis for lambda equals to ax over d is by letting, let's see, let's let x and d constant. Sorry. We want to see the interference pattern. Why I let x and d? I'm going to rearrange the formula. I let x equals to lambda d over a. Okay. So we have already let lambda to be interfered just now already. All right. So right now we let lambda and d to be constant. So what we're going to change right now is a. So if you look over here, x and a, they are a inversely proportionate relation. Means if x my head's a bit haywire right now. If x increases, memang, so sorry class. I think I'm a little bit need to have a little timeout in a short while. When a increases, x will decrease. Which means when the source gets closer, all right, the interference pattern will decrease, means that we will see more pattern. All right, so a increases. So right now, how am I going to make a increases? I'm going to use back green because it's more obvious to see. All right, so right now, my separation, this is my A. My separation between source 1 and source 2 is actually 1500 nanometer. My separation between the two crests is 1740.5 nanometers. So I'm going to, just now what we were saying, increase, all right? I'm going to increase the distance between the two sources. So I'm going to bring this further away from each other, and I'm going to see the interference pattern. Our hypothesis is that x will decrease. X decrease means that this pattern should reduce. And as you can see right now, all right, over here, this is the original length. The interference pattern, the constructive pattern that we can see on the screen has already decreased. So we see more interference pattern on the screen when the distance between two separation actually increases. So I'm going to increase this even further. All right, when I increase this even further, you would actually notice that the constructive part is actually getting closer to each other. Destructive is also getting closer to each other. Now, I'm going to explain a little bit regarding sound wave. Okay, so if I were talk about the sound wave, all right, this sound wave is similar to the sound wave in the school speaker. So if I were to put this to constructive here, because there's no screen measured, okay, so what happens here is that if I were to move two speakers further away from each other, all right, my X should decrease. So when you move two speakers further away from each other, so those who's in PA system, please do take note. When you move two speakers further away from each other, you will actually have more constructive interference pattern. Meaning means there are more places that will actually hear a clearer sound. If you bring two speakers closer to each other like this, the constructive interference pattern is actually very far away, whereby there's a very huge area where people can't hear clearly. All right, depending on how you want to locate it, unless you just want to consider it as a single source. All right, a single source, which means there is no interference pattern. Okay, so regarding the speakers, we're going to talk in a short while back again. All right, so and then the next analysis is where X is, all right, we let lambda wavelength and A to be constant. Okay, so the X will be directly proportionate to the distance between the source and the screen. I can't show that on the simulation. So as the distance between the source and the screen actually increases, the interference pattern will increase. So in terms of light wave, all right, when the source and screen, all right, when the source and the screen gets further away from each other, gets further away, so what will happen is that X will increase as well. When X increases, the two constructive interference pattern will actually increase. So when increase means it will actually I shouldn't say source and a screen. Okay, in terms of sound wave lah. All right. When X increases means that the how to say the loudness pattern will actually get less. Or if it's light wave, we will see less patterns. All right, we'll see less patterns on the screen if it's light wave. Okay, so let's get back to here. All right, so this is the analysis in terms of the graph. What I analyzed just now was actually in terms of conceptual understanding. Okay, so I think I'm gonna take a quick give me a quick 4-minute rest, all right, to rest my throat and my brain for a while. And then after that, we will come back to analyze the interference of water wave and light wave. All right, so I'll see you guys in another 3 minutes. All right, bye. All right. Okay. So, all right, let's continue on with interference of water waves. So I specifically already took out some pictures out from my previous notes that I used and also from the textbook to explain to you guys how does interference of water wave looks like and what you have to take note of. So interference pattern of water wave is produced when two coherent source of wave superimpose. And remember, coherent means that they have the same frequency and they have the same phase constant. Phase constant memang you have to memorize lah, okay? Because they only introduced the definition for phase constant in pre-U level. Okay, so here source 1 and source 2 is considered as a coherent wave. Why? Because the source comes from this motor and it's connected to this wood, and then the two deeper is connected to the motor. So it is considered to be a two coherent waves. So the water wave interference pattern shows the resultant constructive, right? These are the constructive interference pattern and the destructive lines, right? So here is destructive lines. Okay, so for the ease of discussion, the wavefront of the crest is represented by a full line, all right, while the wavefront of the throw is dotted as a dotted line in the pictures inside the textbook also lah. Okay, so over here, all right, this is another picture from the textbook. The spherical dippers produces two circular waves. So this one doesn't uses the wooden plank. It's actually directly a metal that's connected to a electrical motor over here. Okay, so this is the interference pattern of water waves. So this is from the textbook. So the interference of water wave pattern, all right, this is the line with the interference of the bright and dark areas, or the areas that I used to call just now is calling it as a fringe. All right, this is the uniform gray color line. So this bright area, right, this bright area over here, all right, that is a crest overlapping a crest, so that's constructive interference. This dark area is a throw overlapping a throw. This area is the throw overlapping a throw, so you get a constructive interference as well. Here is a crest overlapping a crest, so that's constructive interference. But this gray line, all right, this gray line is where a crest overlaps a throw, and you will be a destructive interference. All right, so in terms of if it is at the seaside, if there is a ship located at the destructive line, all right, the destructive interference pattern, this area is actually calm. All right, this area is actually calm. But if a ship is located at this location, all right, the part where constructive interference happen, the ship will actually goes up to a maximum amplitude of the sea wave, and then it will go down to the lowest amplitude of sea wave and up again and down again. Why? Because it's constructive and destructive interference. All right, so please do take note on this. Okay, this is a question that they used to ask, I think, quite some time ago. All right, so interference of light wave. The picture for interference of light wave is like this. All right, we have a laser pen that's actually clamped to a retort stand, and then another retort stand to clamp at a double slit. All right, so here, all right, so over here what we have is actually a double slit. I'll show you guys when we're back in school again. All right, so a double slit is actually where a piece of paper or cardboard that has two very tiny slits, very fine line of slits over there. Now, remember our formula is lambda equals to ax over d. This a is the distance between the slits. So a is actually from slit number 1 to the slit number 2. All right, so normally in experimental wise, all right, in apparatus wise, they will give us and tell us what is the value of a. Okay, so interference of light wave when an incident light wave passes through a double slit, the interference pattern produced as a result of the superposition of the two emerging light wave from the double slit. I've shown you guys just now. Now, our formula lambda is actually the source of the light wave, all right, because V equals to F lambda. So the frequency of whatever laser color over there will also represents the wavelength of the laser pen. And then A is the distance between the two separation of slits. Capital D is from this double slit to the screen. All right, that's capital D. And then on the screen, you will have interference pattern like on the right-hand side. The distance between two consecutive dark fringes or bright fringes is your X. All right, so the distance between the laser pen and the double slit has no relation at all in the interference pattern. I repeat, the distance between the laser pen and the double slit will not interfere with X, because the only distance that is affected is from the double slit to the screen, from the source of the two coherent wave. All right, the two coherent wave is at the double slit, not from the laser pen. The laser pen is one wave only. All right, so Young double slit experiment. All right, where is my okay? Young double slit experiment uses monochromatic light. So please do take note. Monochromatic light means a light wave with one wavelength only. All right, so if we are talking about the sun, all right, the sun is actually white color. And white color means you have the 7 rainbow colors. So the 7 rainbow colors is not considered monochromatic because there's 7 wavelength over there. There's multiple wavelengths over there. So mono means one. Monochromatic light means light wave with one wavelength only. So laser pointer, all right, laser pointer with a red laser pointer, blue laser pointer, green laser pointer, they are single wavelength, single frequency light wave. All right, so they are monochromatic light. The double slit must be very narrow, 0.05 millimeter, 0.5 millimeter to produce a clear interference pattern, because the wavelength of light is also very small. All right, the slit must be small because the wavelength of light is also very small. So when the light from the monochromatic source passes through a double slit, two sources of coherent light are produced. See, the first part is talking about it must be monochromatic source. All right, the monochromatic will satisfy the same frequency. So when it passed through the double slit, the two sources are considered as coherent. Coherent means that the frequency is the same, and then they are at the same phase. They are constantly having the same phase, which means crest and crest, throw and throw all the time. All right. So the interference pattern consists of alternating bright and dark fringes that can be seen on the distance screen. So this one is actually what I mentioned just now. Bright fringes, because we are at light wave, it's constructive interference. Dark fringes is destructive interference. All right, so this is mentioning about light wave. So interference of light wave pattern. All right, here, smaller distance of separation of the slits. So X is actually smaller. When X is actually smaller, here, okay. Not X is smaller. Smaller distance of separation. A is smaller. From the formula of lambda equals to AX over D, they are side by side over here, so which means A is inversely proportionate to X. When the smaller distance of separation of the slit A decreases, X will increase. So X means the distance between two consecutive bright fringes, this is X, will increase. So when it increases, the pattern that we see is actually less 1, 2, 3, 4, 5. There's only 5 bright fringes that we see. When the distance of the separation of the slit is large, A is greater, because it's inversely proportionate. The X distance between two bright fringes will decrease. When it decreases, we see more interference pattern. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We see 10 interference patterns. So we'll see more patterns. That is what it meant by my message just now. Okay. So that is regarding light wave. Now we're going to talk about sound wave. Whenever I talk about sound wave interference pattern, I'll always relate back to assembly in the hall, right? Because in the hall, we actually use two speakers. Now, when we use two speakers, they are connected from the PA system room. All right, so they actually comes from the same source of sound. So when they actually come out from the speaker, they are considered as two coherent sound wave because the source of the sound that's playing is actually from the single laptop that's inside the PA system room. So over here, all right, interference of sound wave occurs when you interact on the basis of principle of superposition to produce a pattern of alternating loud and soft sound. So, okay, after explaining this, later on you understand now. When a row of students, all right, let's just say here is the school hall. We have our speakers located here and here. And then we have the Form 1 sitting here, followed by Form 2, Form 3, Form 4, and Form 5. And I know normally there's a row of prefects sitting in the middle of the boys and the girls line. Now, what happens here is, I'm going to erase off the Form 1s to Form 4s and Form 3s. So what happens here is our formula for interference is lambda equals to AX over D. So lambda is actually coming from that audio signal generator, which means the wavelength and the frequency is fixed. Now, when the distance between the two speakers is actually our A, let's just say I have a row of students sitting on the front and I have a row of students sitting at the back. All right, this is the stage. So what happens here is that when the wavelength is the same, this is D1. Here's where the prefects are standing. All right, so that is actually D2. So we know that what we're going to see is actually the loud and bright, because here, this is actually loud sound, this is actually soft. So loud and soft, loud and soft. Okay, so what happens here is that if A is fixed, D is actually constant. So my D is directly proportional to X. So when D, the distance from the source, the speakers to the students is smaller, the X is actually much more smaller. So which means the front row of students, all right, they should be able to hear more clearer sounds, alternating students. All right, the distance, the loud and soft is actually very, very obvious. All right, but for students who's actually sitting further away, all right, further away from the speakers, your X actually increases, which means the students can hear loud and soft, loud and soft, and then loud again. The distance X actually increases. So when it increases, which means there's very huge range of students that will hear soft sound, and there's also very huge range of students who's going to hear loud sound, but it's not as much as the student in front who can hear it much more clearer. All right, that's the reason why when you're actually standing at the back of the hall near the main door that time, you can't really hear it very clearly. Why? Because your distance D has already increased. Your X, your interference, the distance between two constructive the loud sound and soft sound has also increased. So it's going to be even much more difficult for you to hear very clearly from the back of the hall. Okay, so then what about if you were to, I think using the explanation should be clear enough for all of you already lah. Okay, so the two loudspeakers are the sources of the two coherent sound wave as they are connected to the same audio signal generator. In our school case, is the laptop. So a student will hear an alternating soft and loud sound if he walks along the straight path X and Y at a distance of D from the speaker. Now, please do take note, what I'm mentioning here is actually A. We haven't even mentioned about the frequency. If the frequency is low, the wavelength is high, then it's going to change whether the loud sound or the soft sound will be more obvious or not. All right. So the alternating soft and loud sound is caused by the interference of the sound wave. All right. So you have to analyze back in this formula if you want to get whether you're hearing the loud or the soft sound. Okay. Please, Form 4, Form 5, after this, don't complain that you are sitting at the destructive interference location when you can't hear the announcement or the things that is being mentioned in the assembly. Yeah? All right. So in case of this situation, all right, from audio signal generator to two speakers, all right, that is your A. This location is the A. All right. From the loudspeaker to the position where the microphone is being moved, that is capital D. And then the microphone will move along the loud and soft sound. All right. And then we can also use a tablet which is connected to the loudspeaker either via Bluetooth, all right, or through wires. Okay. So the tablet with a sound generating application, this is actually the constant wavelength, all right. And then the sound speaker will actually be two coherent sources, and then another tablet that actually measures the loudness of the sound in decibels. So here, A is the distance between the two loudspeakers, D is the distance between the loudspeakers and along the path where we are trying to detect the sound wave. Lambda is the wavelength of the sound wave influenced by the frequency of the generator, the audio signal generator, and X is the distance between two consecutive positions where loud sound is being heard. So loud sound corresponds to constructive interference, while soft sound will correspond to destructive interference pattern. All right, so applications of interference of waves in daily life. So knowledge on the interference of wave is widely used in our daily life. Example is this application of water waves. Mana my Okay. So here, in front of the ship, right, there's actually a bulbous bowl, right? It generates water wave which interfere destructively with the water wave around the hull. Right. So this causes the water around the ship to be much more calmer, thus reducing the water drag. So here, in order to reduce water drag, all right, they actually have this bulbous bowl, all right, so that the waters around the ship will always be calm. Will not always be calm. It's much more calmer, especially when it goes to a deep sea region and then there is a storm coming, right? In order to stabilize whatever cargo that's in there, they actually uses this particular bulbous bowl, all right, to reduce the water drag as well. So that is one application from textbook. Next is actually our specs, all right. For our specs, actually, you would notice when you go to the optical center, there are different types of specs actually. All right, they will say whether do you want your specs to be multi-coated, non-coated, single-coated, or do you want to have the blue ray filtration or whatsoever. All right, now coatings on the surface of an anti-reflection lens will actually causes reflected light to interfere destructively because lens has two layers, the outer layer and the inner layer. So when light ray enters, all right, when it moves from a few densities, different densities, it's supposed to undergo refraction. When it undergoes refraction, they will interfere. So the coatings on the surface will allow it to interfere destructively, therefore helping to improve the vision. All right, so that is actually in terms of specs. Next is actually headphones. I'm sure some of you are on headphones right now. If you will notice some good quality headphones, when you're playing a music, when you take out the headphones from your ear, you can actually hear the sound because of diffraction. But when you put the headphones onto your ears, you will notice that the whole sound is very loud. But if your friend is standing beside you, they cannot hear the sound or the music or very, very soft. Why? Because the microphone and the transmitter system in the headphone actually use on airplanes or our normal speaker type will produce sound waves which will interfere destructively with the surrounding noise. All right, so even when we use our headphones, right, we would notice that sometimes we can hear the music very loudly, but people around you can't really hear it that clear. It's because outside they are undergoing a destructive interference pattern. All right, the constructive interference pattern all focuses inside your head. All right, so that is actually for interference. All right, that is the conceptual part. Okay, so due to the time, all right, I'm gonna explain this question. The rest of the question you guys can attempt yourself. Um, wait, I want to cover one more part for wave. If you don't mind, give me about 5 to 10 minutes. I'm just going to go the electromagnetic wave over here. I'm going to explain a brief part. Electromagnetic wave is a very straightforward part, which I think you guys can actually read it up on yourself. But there's one situation that I want to explain regarding electromagnetic wave. So electromagnetic wave comes from the two words electro comes from electric field, whereby magnetic obviously meant for magnetic field that actually oscillate. Oscillates means it vibrates perpendicular to each other. So the electric field and the magnetic field are 90 degrees from each other. All right. So electromagnetic characteristic is number one, they are transverse wave. All right, which means that the wave propagation and the particle's vibration is perpendicular to each other. All right, electromagnetic wave do not need a medium, which means they can propagate through vacuum. All right, it can propagate through vacuum. So it travels in the speed of vacuum, which is 3 times 10 to the power of 8 meter per second, which also corresponds to the speed of light. So it moves with lower speeds in any medium. So far, the speed of light is the fastest that they have detected so far. Okay, so whatever that is non-vacuum, it moves slower. Electromagnetic wave will move slower. So it shows the phenomena of reflection, refraction, diffraction, and interference. Do take note. Under suitable conditions. All right, so for the wave of v equals to f lambda, because it moves at the speed of light, which is c, 3 exponential 8 meter per second, this formula becomes c equals to f lambda. Okay, so over here, the word continuous spectrum means there's no specific boundary which separate two adjacent type of wave. What does it mean? This is the electromagnetic spectrum. All right, electromagnetic spectrum, we have gamma ray, which is the highest frequency, lowest wavelength. Why do I say highest frequency, lower wavelength? Remember just now we talked about the wave speed equals to f lambda. And for this case, electromagnetic wave move at the speed of light. So c equals to f lambda. This is constant. Speed of light is always 3 times 10 to the power of 8 meter per second. So the frequency will be inversely proportionate to the wavelength. So the frequency increase, the wavelength will drop. So gamma ray has the highest wave frequency, followed by X-ray, ultraviolet ray, visible light. This small gap here is visible light. Visible light is the only one that we can see. Then infrared ray. Infrared is the one that we use to control our aircon, our fan or light or whatever it is, or TV, all right, that's using infrared ray. And then followed by microwave and radio wave. So some of you will be answered. You don't have to memorize the value of the wavelength. You just have to remember radio wave has the highest wavelength. Gamma has the lowest wavelength but highest frequency. Now, what do you need to memorize? You need to memorize this spectrum. The flow. Gamma ray, X-ray, UV, visible, infrared, microwave, radio wave. You have to memorize the flow. All right. Over here, it says the energy carried by electromagnetic wave is directly proportionate to the frequency. Energy of the electromagnetic wave is directly proportionate to the frequency. Why is it directly for frequency? Form 4, you will learn it next year during quantum physics. So this means that gamma ray and X-ray carry large amount of energy. Gamma and X-ray has large amount of energy. So this wave need to be handled properly as not to endanger the users. All right. So the rest of it, I think you can read and understand it by yourself. All right, because it's quite straightforward for this. You just have to memorize what is the source of the electromagnetic wave and what are the applications of it. Okay, normally they ask more on this spectrum. Okay, so due to the time constraint, I'm gonna stop here since all of you have this PowerPoint slides that I have combined. So I considered that you guys will be able to read through that. I specifically arranged the whole entire flow for the slides over there. All right. So do you have any questions for me? Ada soalan? The questions you all try to do it out yourself since I already posted the answers there also. All right. Brian, no questions. All right. Since you have